Hello, everyone. Welcome to another Kent Seminar. Today, we have the honor to host Professor Xiaopeng Li. He's a professor at the University of Wisconsin-Madison in the Civil and Environmental Engineering department. Professor Li used to be Professor Wu Yang's student, and he graduated in 2011. He earned his bachelor's from Tsinghua University in Beijing, China. And then his master's and PhD from UIUC, along with a master's in applied mathematics. So allow me to say a little bit more about Professor Li, because there is a long list of achievements. Basically, his research interests are automated vehicle traffic control and interdependent infrastructure systems. But he's also the director of US DOT National University Transportation Center, National Institute for Congestion Reduction, and he also founded the Connected and Autonomous Transportation Systems Lab. He has published around 90 peer-reviewed journal papers, very high-quality ones, and he also led research projects up to $20 million. He's a recipient of the National Science Foundation Career Award, and he serves as an associate editor or editorial board member for a lot of journals. He's also a member of many TRB committees, like the Transportation Network Modeling Committee and the Traffic Flow Theory Characteristics Committee. And the list goes on and on, but I'm just going to stop there and say we're so happy to have you here back on campus, and please join me in welcoming Professor Li.
Thank you, Rana. And thank all of you for being here, including those online. And it's my great pleasure and honor to come back to University of Illinois and have this opportunity to exchange our research and thoughts. So today I'm going to talk about some of our work, including both models and field experiments regarding the safety, mobility, and stability of automated vehicles. So, this is my name. I just wanted to mention that some people also called me Shaw, and there was before that another professor at my institution had exactly the same name, and we received emails and everything from each other. And once he received a big award, with a nice plate with my picture on it. So anyway, I graduated from University of Illinois, great institution here, and then I went to South to Florida, and then came back to sweet home from the Midwest to the Midwest. So if you look at my pictures 12 years ago, when I was graduating, working with Dr. Yanfen Ouyang, a great advisor and professor. Now I actually joined the UW-Madison last year. Look at the two pictures. I don't change much, right? Except a bit more wrinkles and a better smile. That's biased. Here we go. Anyway, coming back to the research. So, you have heard of the technologies, connected vehicles, automated vehicles, or say CAVs. And people put high hopes on the benefits of these technologies. For example, it's going to improve the safety significantly, reducing over 90% of crashes. In terms of mobility, it can improve the capacity by multiple times, and energy efficiency improving over 50%. Lots of good expectations and hopes for this technology. And what was exciting was that this technology was demonstrated like 25 years ago in California highway. We have vehicles connected and automated, and demonstrating some of these potential benefits. And back then, I think people's vision would be like this. So in one day, our traffic could be like that. All the road users share the rights of way harmoniously without stopping in the intersection, although I'll be there to walk across the intersection like that. But it's a computer graphics, don't worry. It shows an idea, at least from the vehicle automation perspective, how the transportation system that people back then would envision. So let's look at throughout these 2-3 decades what happened, and lots of exciting developments in the real world, right? Lots of deployment of automated vehicle technologies. You've seen all these different brands of vehicles that have automations and provide us various services, including ride sharing. Besides passenger cars, you would see like shuttle buses. Micro transit shuttles and trucks, and some small delivery robots, and even for restaurants, right? They try to provide robot waiters, waitresses, right? I saw this in one of the hot pot restaurants in Madison. I'm not sure if you guys have it here. Please check it out. So all these technologies are automation and are about transportation. Very exciting. So overall, I call production automated vehicles, they have grown a lot. So these are the vehicles that are running on our road, right? From 2% of market penetration rate to around 10% at this time, and a projected 40% in 2040s. If you look at the newly produced vehicles, 92% of these cars have capability of level 1 automation, that is longitudinal control, and 50% of these new vehicles, at least they have a trim about level 2 automation. That means both longitudinal and lateral control. So, and the particular technology that people refer to for this school of technology is called Advanced Driver Assistance Systems, or ADAS. And the longitudinal control component is often referred to as adaptive cruise control, ACC. All right, so which is basic control, controlling the subjective vehicle to follow the preceding vehicle automatically, depending on the spacing, speed difference. Today I actually had a ride with Akash, and his vehicle had this function. It's just like you can set it up like cruise control, but on top of that, you can decide the headway of following, right? Normally you're gonna see 3 or 4 bars on your dashboard that shows the headway that you set to follow the preceding vehicles. I just wonder how many of you have this kind of cars and or experience them? Okay, all right, almost half, right? I would consider. So great, looks like this is not a futuristic technology. And let's look at how well they perform against the high hopes I showed in the first slide. About safety, all right, at least from the self-reported data from companies like Tesla, the safety improvement is significant when the system is activated. So it looks like they can improve, you reduce the crash rates by 80 to 90% if you just look at their self-reported data. Despite that, we know that we are in the right trajectory to improve safety, and they put safety as a focus, right? So they're on the right track to proceeding to the 94% of crash reduction target. What about mobility, right? Let's just narrow it down to the capacity. So we actually collect field data for human-driven vehicles and ACC, this technologies, vehicles from different automakers. We compare we plot out their flow rate over density, and that the highest point is about the capacity. And against the high hope about the capacity improvement, looks like they're more or less the same. And even if you put it to a longer headway, the capacity could be even lower than human-driven vehicles. So this is far from the hope of multiplying the capacity, right? So we're still far from that target. What about the energy, right? Again, you can collect this vehicle trajectory data, either the location trajectory or speed trajectories from HV, human-driven vehicles, and ACC or AVs, and then use a few consumption models, energy consumption models to study and compare the energy consumption. We found out that ACC energy efficiency is slightly better than HVs, but not far away, but it's still far away from the 50% or higher improvements benchmark. So there still remains room for quite some improvement. So from what we observed in the industry and in the deployed technologies, we see that people put lots of focus on safety, and they are trying to push in a safety better and better. But the mobility is like they haven't improved it that much. You guys have ridden some of these vehicles, right? And energy is also of the secondary consideration. So this is slightly different from, actually, this is quite different from the vision that we have from a transportation system engineering perspective, as I cited before, right? We have that vision of so-called cooperative driving automation. That is improving all this performance at the same time, right? So, one way to do this is to have these vehicles not only just individually automated, but also coordinated, make them cooperative. For example, one example is like to control these vehicles. This is a time-space diagram. You can think about this as a segment leading to intersection with alternative green and red faces, and you can platoon these vehicle trajectories and control them smoothly that they will pass the intersection, just as the animation showed. This is going to give you the overall improvement of not only safety but also mobility and energy. So this is our vision, and I believe in the past decade there has been, like, if not thousands, but there will be hundreds of papers talking about how to optimize vehicles in the system and control their trajectories only on computer. But why haven't we seen this kind of technologies employed in the real world? I was wondering that question. So I actually built the lab, as Lamar mentioned. We started some initiative of building some hardware. Then I would try to say, on top of the research paper, let's try to implement some of this. And first thing is, we're given one trajectory. We want to have a vehicle to follow exactly this trajectory, right? Let's just do this simple task. All right, I'm going to give you a vehicle the input of like reference trajectory. This is represented in terms of a speed profile, speed over time, right? This is the orange dots are the speed profiles we want this vehicle to follow. And we let it run for 2 times or multiple times, and these are 2 runs. And you see red and blue curves are 2 runs. They are quite different from the target trajectory. And even different runs have different trajectory shapes. So with this, if you implement CDA according to the computer simulation, you would think that, imagine disasters would happen, right? Lots of collisions will happen. So that brought our group to the attention of the actual control and the ideal trajectory we want vehicles to produce. Right, we have ideal the smooth trajectory, but due to the limitation of existing vehicle control, you may not be able to have this vehicle to follow the target trajectory exactly. There will be, errors over the time. What can you do? Maybe you can say, okay, now we can add a safety buffer, right? As long as we add sufficient safety buffer to absorb the errors, we can still do this kind of control, right? Then this is going to bring a problem. So how much safety buffer we need to add there to make the system safe, and how to quantify such safety buffer, and would that impact mobility? Would that impact safety, right? So in the past, if you're familiar with transportation systems research, safety and mobility is like are going parallel on 2 different tracks with different approach. But this is an opportunity that we can integrate the perspectives from both safety and mobility, as well as energy and stability in one shot. So let's look into how the imperfection of the automated vehicle control would lead to the trade-off between these different elements. And if we know the limitation, how are we going to improve the system? So I'm going to talk about some of our studies and understandings, first from analytical model, and then field test verifications. And then finally, I'm going to talk about some ongoing work about how we can improve the system. So let's start, with a simple model. When I started something new, I wanted to look for the simplest model that can explain a first order phenomenon that we observed in this real world testing. So I chose to look at a very simple model. So many of you might have learned it from traffic flow class about so-called car follow model, right? So let's just look. We started from a very simple first-order car follow model. If you look at the system, there is only two vehicles: subject AV following a preceding vehicle, and I'm going to use x0t to denote the location of the preceding vehicles from bumper at time t, and y0t to denote the location of the following subject AV at time of t, and x0t and yt are two trajectories if you vary the time t, right? And then the first one dot means first order derivative speed, two dots mean acceleration, right? So the car follow model or the vehicle control is as simple as this. I want to control the second vehicle's the subject AV is acceleration in this form. There is a sensitivity factor times two terms. The first term is basically x0 minus desired. It's the first time is x0 t minus L minus y0 t. It's actually the gap, the extra gap between these two vehicles. And the second term is I call the safety buffer plus some extra time lag gap to absorb the speed. So safety buffer times tau, which is the time lag, times the following vehicle speed. So this is like an ideal distance or spacing that these two vehicles want to follow, and this is the extra spacing. And you look at their difference in area, and you want to control acceleration to close this area so that this second vehicle will try to follow the preceding vehicle with an ideal spacing. All right. So in this model, it's very simple. It's linear, and it only has three parameters: k, like control sensitivity, delta, safety buffer, tau, like reaction time, right? And with this, actually can loosely relate delta with safety. If you need a long safety buffer, then this control is not very good, and maybe that brings down the safety. Tau, if it increases, you're going to have a longer falling time headway that is associated with mobility, and kappa, if that increases, chances are the stability can drop. I mean, it's not exactly like this, but at least these three parameters and their combinations will decide the safety, mobility, and the stability. And the nice thing is it's such a simple model, and it integrates all these three aspects. All right. And then I was thinking, all right, I have this model, but if I were the person to design this vehicle's control logic, AV, how would I do, right? I know this is a form, but how do I decide the values for this lambda, tau, and k to make sure that the system is safe and also efficient? All right, so then I introduced this concept of robust control. So sort of like, what does that mean? We don't know what the first vehicle will do, right? The first vehicle could be a human driver, or could be, could be another automated vehicle, but you really don't have control about how the first vehicle will do. It can have all kinds of trajectories, right? Let's see. We consider all possible trajectories and movements that the preceding vehicle can do, and we want to make sure that the subject AV will always be safe, will always not have a collision against the first vehicle. So that comes with a robust sense. You basically exhaust all possible trajectories of the preceding vehicle and find the worst case, and you want to make sure that worst case this vehicle does not touch the preceding vehicle's trajectory, right? And so essentially you're just going to compare x0 t minus L, which is a rear bumper location of the preceding vehicle, and the y0 t, which is the front bumper location, or you can add a safe sort of small buffer on that. So you want to make sure that this location is always greater than this location. Therefore, these two vehicles always have a positive gap that ensures the safety. And you want this equality to be tight in the worst case to make the mobility and efficiency the best. All right. So and the idea is y0 may overshoot and encroach into this safety buffer from time to time due to the imperfect control. And we want to make sure that this overshoot never exceeds safety buffer. So that's the purpose of this safety buffer. And if you translate this into mass equation, it's going to be like this. Don't worry about the mass. You know, it basically means that we need to design the delta to absorb the all the overshoot across all circumstances. We have some very general initial condition and some vehicle dynamics, and we don't assume any trajectory form of the preceding vehicle. We just consider that preceding vehicle has acceleration limits and speed limits, right? Which is true for real-world mechanical vehicles, right? But it can decide its own moment within this constraint. So it comes with the form of robust optimization, right? All right, so it's a complicated equation. You know, it's the decision variable is like an infinite number of decision variables, and differential equations are really complicated. You know, you would think it would take tons of effort to solve it, but you know what? I spent quite a lots of effort sitting like for 2-3 a.m. for a few nights and used the MATLAB, and eventually we solved it analytically. All right, this may look complicated, but this is an analytical solution. All right, so it's really, it's not that easy to solve a mathematical programming problem analytically always, but we did that. Well, actually, and this is really complicated, but you know, you can look into some simpler or special cases which are still very representative. You know, when some variables is in a certain range, let's say this means basically the speed range compared to the acceleration range. This ratio is, if it's greater than certain value, you're going to reduce the analytical equation in this form, and you can theoretically prove that. You know, the relationships of how delta changes with kappa and tau, and it's so basically delta, as delta goes to infinity, well, actually it means delta is going to decrease, and the decreasing trend is convex with kappa and tau. That means, okay, if you want to increase tau, you have, if you want to basically decrease delta, you have to increase tau and kappa. That somehow represents the trade-off of relationship. All right, so delta, remember, if you want to increase it, make the system safe, you have to, all right, if you decrease it, make the delta tighter, all right, that means you need to have better safety functions of the technology. You probably have to increase the tau value and increase the kappa, which will result in not as good mobility and not as stable system. All right, and you can analyze another special case when this value goes to the other side, and you can prove this you know, same relationship holds. And for other general cases, you know, because that's a relatively simple analytical equation, although you cannot prove their relationships analytically, you can still plot out all the cases, and you can observe that you know, basically, loosely speaking, this delta decreases with kappa and tau across all cases. So that result is quite elegant. So what that means is, let's just look at the relationship between tau and delta. So basically, if you want to improve the mobility, that means we probably need to squeeze the tau a little bit, make it shorter. And then with the same technology configuration, you'll probably need to increase the delta. That makes the safeties more demanding and stringent. All right, that's one aspect. And also, you know, I'll just skip the math here, but you can do some, because this is a linear model. If it's a linear model, you can use the classic frequency domain analysis to analyze the stability. You know, basically, you can look into, we call it, if this is a first vehicle's speed variation, and this is a subject AV speed variation. If you look at their magnitude, and this, let's say, y absolute value of y is the oscillation magnitude of the subject AV speed, and absolute value of x is that of the first vehicle. These two ratios is determined by a parameter called TF, and you can analytically solve it in this form. And you know, if TF increases, that means this ratio increases. That means this system is less stable. And And basically, you can theoretically prove that this tall, that's actually an indicator of mobility, and has inverse relationship with this tall F. If you want to make the system, so basically you have to increase the tall to make the system actually more stable. Or if you, it's like the tall going up, but this is going to go down, and if you have to reduce the tall, you're going to make the system less stable. All right, and we also look into another parameter that is sort of like a dominating magnitude, is like what is going to be the oscillation cycle of this speed profile. So that's if the system runs like that, and you also find that if you want to reduce the tall, this oscillation cycle is going to reduce. What that means, if you reduce the head weight, all right, I'm going to have a bigger oscillation amplitude of the segment of vehicle in shorter cycles. That means you're going to have more abrupt deceleration and acceleration, which means worse stability and more fuel consumption, right? All right, so with this, we have theoretically proven that, with that model, if you want to design a first order model and make it safe and efficient, then you're going to find the parameters have this kind of trade-off relationships. And that means if you want to improve mobility, you have to sacrifice safety. If you want to improve mobility, you may have higher traffic oscillations and higher energy consumptions. And I actually did this pure theoretical work, and you would think that I think this is the only paper over the 10 years that I wrote it myself. I was, for most of my work, I just do the talk, and my students do the actual work, and I'm just So, and then one student came to me and he said that, all right, he said he didn't believe me, or this is just numerical work, right? You can't do anything, right? I thought, okay, now you're smart. Now we have vehicles. Why not you bring them out to the road and give it a test to see whether it's true or not? He did that. All right. So we have lab vehicles. These are actually retrofitted from a commercial production vehicles hybrid, and we have ACCs. We retrofitted it, and we added some of the components to collect data, like high resolution GPS, and we have these vehicles drive along the public roads, of course with drivers there, but we turn them into the ACC mode. Maybe some of you have done that if you have ACC cars. And we did a bunch of experiments, like 2 cars, 2 AVs following each other, 2 AVs following another AV, right? So, and we actually have different speed profiles. So my student know how badly I drove. So he actually asked me to just sit in the passenger side to record the data. So I just had a timer and told the student what speed you should switch to, and he did that. And we just basically switched the speed from 55 miles to 53 miles and come back to 55 miles, and doing this kind of oscillating testing with different period of time. And so we got the speed data profiles like these. These are just like you gradually increase the oscillation amplitude, and we also test the vehicles at different headway settings, right? Remember the vehicles we have had 4 different headway settings, all right? And these are the testing that we did for 3 vehicles, and we changed sort of like a vehicle oscillation periods to find which period is dominating, which period would give the system the worst oscillation. All right, so here are the results. So basically we collected data, and we could bring the data and try to fit the data with the model, the first order model I had. So you can do some regression to get to the parameters like tau, kappa, and delta. And the fitting are pretty good. Look at this, right? You just have a first order linear model that is not perfect, right? But still you could get quite good fittings. That means, okay, this model at least will reasonably explain the trade-offs, at least from the first order, right? And if you look at their, with the headway changes, all right, headway from 1 is the shortest, 4 is longest, you're going to see tau increases. Actually this K decreases, and delta, this is kappa, sorry, it's kappa decreases and delta decreases. These are exactly what our theory predicted. For different speed range, we try to have the vehicles run at different speed range to capture some of these nonlinear areas. Still, you see low speed and high speed, this relationship is exactly the same as model prediction. And here are some results. Headway settings that shows different talls. That means okay, different headways corresponds to different talls in our model. And then headway versus fallen gap, right? These are some of the intermediate results. So these graphs show the trade-off that I actually predicted in the theoretical analysis. So tall decreases, delta. As tall increases, delta decreases at different speed range. There is some nonlinearity, of course, that our first model, the first order model doesn't explain, but at least from the first order, you can see that case decreasing trend has been captured. As tall increases, the kappa decreases. Actually, for both speed range, this kappa actually overlap very well, less nonlinearity. And we also tested stability. All right, so basically we have different headways and we have different different oscillation cycles of the vehicle's speed variation. And we actually recorded that TF, that transfer function, which is the amplification from the lead vehicle's oscillation to the following vehicle's oscillation. And the maximum corresponds to the dominating frequency. You see, as the headway increases, the P value increases and this TF value decreases. What does that mean? You're going to have a longer oscillation period and less oscillation amplitude. That means if you can afford a longer headway, the vehicle oscillation becomes less and less prominent. Of course, all these are still unstable. You can criticize the auto manufacturers. Okay, why do you still have these unstable models? If this value is greater than 1, it increases the speed, right? So if you have 10 of these vehicles following each other, you're going to create a chaotic scene, right? So at this, we also tested the data from tested the models with data provided by a different institution, and we have this consistent finding. So now this student, okay, he's Tom Shi, and he's ran a postdoc at the University of Michigan. He said, okay, then looks like this is interesting. All right, so maybe the theoretical modeling does help sometimes, right? Not always, but this time it explained what happened. All right, so now we know there is a trade-off. All right, it's actually this trade-off is somehow intuitive to me originally, so that's why I wanted to show off that theoretical work alone to my students, and I was pretty confident, and then I argued against it. So because you can imagine that if you want to have two vehicles follow closer, then the following vehicle needs to react more agile, and that may create stability issues, right? So, but the nice thing of this work is it define the problem rigorously, and we have analytical solution, and we can also verify that with the field experiments. Now, the next issue would be, how are we going to improve? Are we going to be just stuck here? And if we are stuck here, we're never going to realize the vision we had in the first place, right? We improve the safety while we multiply the capacity. That's never going to happen. So how we can improve the AV technology that we have today to reach some of the visions that our pioneers had before. So of course, if you have this kind of control, as I showed, the vision is never going to happen. All right, you can almost impossibly reduce the vehicle gaps. They're going to collide into each other terribly. So if we do not see maybe the auto manufacturers, they may not want to do anything. One strategy, just leave it as that, and we're gonna have to. It's gonna be a pessimistic scenario for transportation engineers. Individual vehicles gonna have. Then you have to add sufficient safety buffer for individual vehicles, and it's gonna compromise mobility energy benefits against the CDI vision that is dominated by the theory and experiments we showed before. Or we can improve the fundamental control, make it better than that kind of linear control, all right? So one direction that we explore is to really try to improve the control method. So we could use predictive information to use more of a model predictive control, and also we could use some learning techniques to really offset the actual control error and the predicted control values, right? So we did some very early study, just concatenated online learning and model predictive control, and we actually developed some model, but we also did some small scale tests, right? It's just small student project. You could spend a few $100s to construct mini scale connected automated vehicles test bed. This is about $100 or $200, and you have some paperboard. You have a circular, track, right? That costs almost nothing, and then you can add some of the other sensors, and you can use Wi-Fi routers to connect them. So we tried those traditional sort of PID based control and our online learning based NPC, and we found that we can improve a lot of the control error. So you see here, you see a big difference between the actual trajectory, which is blue dots, and the reference trajectory, target trajectory, red curve. And now we close it a lot better. Even with that kind of shabby equipment, that kind of vehicle is really difficult to control. If you worked on it, we can improve that error by 70%. That means this direction is promising, right? And with that, we could move one step forward to do this kind of if you can do them control better, that means you can have shorter safety buffer, and then you can plateau them closer and achieve some of this mobility and energy vision. So we did some experiments for platooning, like formation and split on this small scale test bed. We're not satisfied with that. We, as I mentioned, we built a full scale test bed, right? Our students were really talented, and we built this in-house. Actually, another reason I don't want to tell you what we were short in budget. We couldn't buy the vehicles as a whole. We had to get some components here and there, but that was a helpful experience. We learned the ins and outs of the system. All right, of course, if you have this kind of system, it's a good showcase, right? And whenever important people or nice visitors come, you can show off. But more importantly, you can do some field experiments with this kind of platforms. For example, this is the experiment that we did for longitudinal trajectory control in coordination with signal timing. There is actually downstream of this road, there is a traffic light that is red currently and will turn into green phase. And you have one vehicle here that is a CAV. The other vehicles are just human-driven vehicles, right? So the human-driven vehicles will just drive as usual and will make a stop at that intersection. But this vehicle is smart enough to learn a signal timing plan and will adjust its trajectory to pass the intersection right about the same time. Let's see. All right, so basically this vehicle will just proceed to the intersection and make a full stop. And this vehicle is just do a good timing, does do good timing and pass it without any stopping. Right, you can see it again, it just calculates exactly when this vehicle will leave the intersections, make sure that you can follow the stream, not too long gap, but not stopping. There is another experiment with one downstream vehicle, and it's going to stop there, and you're going to join that time when it leaves, right? So very interesting. Of course, so automation alone may be limited. I mean, you need to have connectivity. That's why we say it's CA, right? So we actually did some work in collaboration with other institutions, and we pieced up our data and did some predictions. We found that production AV energy performance may be even inferior to human drivers in urban environment due to delay of stops at intersections, because it didn't communicate with his intersection very well. They had lots of waste time and energy out there. So if we have connectivity, we can improve it. And also we work closely with the US DOT Cooperative Driving Automation Program. We're actually the first external team that has demonstrated their Karma system successfully at in field tests. We have a joint demonstration I think I should show you a nice video here, but these vehicles actually jointly demonstrated platooning functions in test bed. Already gave you some very nice the news release in ITS Congress last year, and we're also creating some other fancy technologies for low cost communications. For example, you can use a light board and to have like different flashing patterns of these light grids or LED board to communicate some information. That is faster than just what our human drivers can perceive, but and can communicate to most of the critical information for cooperative driving applications. All right, of course, another aspect is we looked into the powertrains, right? Maybe if you make that powertrain work better, more responsive, maybe you can continually improve the outcome. We compared the different powertrain technologies, and we used our vehicles, and these are hybrid vehicles. We already have the data, and then we actually had some ICE vehicle downloaded from the data contributed by other people. And also I had very generous students who was apparently having a better status than I had Chevy vehicles, but they had a nice Tesla. They purchased the full package of autopilot, and they contributed his vehicle. We collected a bunch of the data, and then we used the same system to analyze it, and we looked into the basically did some regression to get these parameters, and we found that okay, if you look at the outcomes, let's just look at the transfer function or oscillation amplification ratio and the minimum headway. So it looks like ICE vehicle has the largest TF, largest oscillation amplification, and the electric vehicle has the minimum of that. That means the electric vehicle is more stable. And minimum headway, they're on the same order of magnitude, but still the electric vehicles the shortest. That sort of validated our hypothesis that EV may do better. If you drive EVs versus ICE vehicles, you will feel that EV responds better. And we collected the data and convert them into density to flow diagram, and we did some regression. You can see the results. So this line corresponds to flow. This red dashed line is a flow and the density relationship for electric vehicles, and the blue one is hybrid vehicle, and this one is ICE AV. And we see that blue one is higher than, that the electric AV, the red dashed line is the highest across most of the density ranges. That means, okay, maybe that has better implication to the to the traffic throughput. And also if you know traffic flow, that the slope is the shock wave. This one, EV can dampen the shock wave, make it milder. So finally, I want to acknowledge all my collaborators, particularly my two of my students, Xiaopeng Li and Tom Shi. And also I want to acknowledge all the major external sponsors. With this, I want to stop on my presentation. I'll be open for any questions. Thank you again for the time. Yes.
Thank you for a nice presentation, Professor. So you started the first, I think in your second slide, you mentioned something about the optimistic expectation of tripling and quadrupling the capacity of highways with the introduction of autonomous and connected vehicles. Could you use this model actually to estimate the actual or the realistic enhancement in capacity? This is one thing. And if we talk about the use of this model, if we can use it to estimate the realistic enhancement in capacity, are we talking network-wide? I mean, are we taking into intersections, or are we talking about just freeway?
Oh, sure. So yeah, this model, basically once the model parameters are given or obtained from the data, you can convert them into from the microscopic headways to macroscopic traffic flow rate and density and speed, and construct a relationship of the macroscopic traffic flow capacity measures. All right, so that we can do that. It's just that I think the key is what kind of data you can fit, and then you get rather the key parameters, right? So so that's one aspect that we can do that. What is the second half of your question?
If we use that model, does it only take into consideration like one street, or can we still maybe use it simulation? I mean, including intersections and the disruption.
Yes, we can. And I mean, this provides an elemental model for microscopic simulation. You can use it to define one vehicle's longitude and control behavior, which is a necessary component for almost all scales of simulation. You can simulate complicated networks, but each vehicle still needs to have an individual model, which you can take advantage from here. Yes.
So you get. Thanks for the presentation, Professor. So I have one question which is related to platooning. So that's something that group we have been working on. How much these parameters would change if you were to model this for trucks, like sensitivity and also the headways? Do you think it is going to increase or decrease? And follow-up question is, you have mentioned the headway in terms of seconds, right? So what is the speed of the vehicles there? Speed of the cars for the headway? Is it like 70 miles per hour? Because I'm trying to get an estimate for trucks. What is the minimum distance that you can go?
Yeah, I can only answer the question for trucks theoretically, because we could not afford an autonomous truck yet. But maybe after you get the test bed, we can verify your problem here. I can only speculate it. So because trucks control is to a certain degree, it's less responsive compared to it takes maybe longer time to break a truck to a full stop, right? So I could imagine that the sensitivity is like K is maybe smaller than, if you want to compensate that, you may want to have a longer headway. That's my speculation. Don't quote on me, and we have to verify that here at this great facility. All right, and next thing is about the different speeds, right? We think the tested the different speed ranges. We have a high speed at like 55 and varying to different speed, and low speed 35 varying to different speed. And the vehicles that we tested could only support automation about 20 miles per hour, and we don't want to have it go too high for safety concerns. So we almost exhausted the speed range as wide as we can possibly explore for in our experiment, and we compared the high speed and low speed results to give us some hints about nonlinearity. But despite that, our first order conjectures and the theoretical results are well supported by the data. Yes.
Okay. Well, thank you. It's great to learn the great things you are doing. That's wonderful. Two questions actually related from what you presented. One is when you are doing this robust control design, and then it seems that you are considering exhausting all those different possible parameter sets. Do you see any potential uniqueness in the solution when you are doing the design? You are doing sort of optimization, right? You're looking for that solution. Is the solution unique? And I wonder if that's having impact on the findings you have. That's one question. Maybe I'll give the second next.
All right, so I'm trying to better understand your question. So you're saying, so is there any unique structure?
Uniqueness.
Yeah, because although it's this is the general solution. If it's really complicated, I have to define some special operators.
Well, maybe let me rephrase my question. I was thinking you have this delta kappa, and then what's the third tau?
Tau, right?
Could there be multiple combinations of these values that are going to yield very similar results? I was wondering.
Oh, yeah, whether these are
It's
correlated
local optimums in the
local optimums.
yeah,
No. It's not this global optimum. It's theoretically proven that this problem is a convex problem. Well, it's linear actually in a way, because the model is linear, and so I think yeah, it's sort of like a linear program. Because the model is first order, otherwise it's difficult. It's analytically solved. If it's analytically solved, that's we use the sum control theory like maximum contrarian principle. So basically, this is a solution of a KKT condition.
Oh, I see.
There's only one solution, so that's it, right?
Oh, that's great. The second question I have is related to the you talk a lot about you talk about sharing a little bit information. So essentially connectivity in a sense. I was just actually curious from the string stability issue that will really be improved a lot by sharing information across vehicles B2B. So I was wondering, like right now you are really considering autonomy, but then a little bit connectivity, but then did you explore that direction a little bit? If we're doing a formation, platooning and so on, that the vehicles are sharing information, would that sort of really improve the current trade-offs you have, right? Right now you have a Pareto frontier between capacity and then safety and then stability.
Right.
I was wondering if how much impact that the connectivity is gonna make a difference to the trade.
Right. So I think if you look at this so if you just look at this linear model structure, it's essentially falls in PID control. It's reactive and
Yes.
based on Markov state. Doesn't have memory of past and doesn't have the information in the future.
Yes.
Right, so that's what most of the car follow model and control is based on. But if you have connectivity, at least you can have a bit more information about the future vehicles' behaviors. If you have that kind of predictive information, you're not going to use this form of control, I guess. Right, so that will do a lot better. But if you just use this form of control, it's just limited by the theoretical prediction. This has to be some trade-off. If you want to push the Pareto frontier further, I guess of course you have to if you can improve this. One thing is if you just look at this, giving you an example, if you can increase this kappa value, a lot, then maybe you can improve safety and the mobility part simultaneous, but that brings local instability issues, and so it's really difficult to work with this kind of model. It's just that's what the theory governs. You have to come up with nonlinear model, predictive model. That's what we did in the second part of the presentation. I mentioned the learning and then model predictive control that adds nonlinearity to it, adds predictive information to it. That information can be provided by connectivity.
Great, wonderful.
Yes.
Just a small question, if I may follow up with Professor Adams. Thank you for the nice presentation. So far you've shown us how to identify putting a buffer with the mechanical movement of the vehicles. But now you brought up with connectivity, there's associated lag of information. How do you embed that in such platform where you have a safety buffer on the physical movement, but also the information movement between the vehicle and whatever module it's connected to?
Right. Yeah. So I'm trying to partition your question. It's like I have connected the vehicle information, and how does that affect the safety buffer, right?
Yeah, because then when you have also a buffer in terms of how fast and how short that transfer of information can maybe change how the vehicle should move safely or not, right?
Yeah, good question. I'll just follow up a little bit about my response to Dr. Young's question, right? Because currently the model, because of the lack of information, you're using more of response-based control. It's like the model I showed, it's linear and it's responsive. That means I don't know, for example, this trajectory, that target trajectory is the deceleration and acceleration. But you don't know that. You always want to get to the equilibrium state, which you project as a line if you're just doing responsive control. You don't, it's basically the responsive control is just equivalent to you have a linear prediction of your future, right? Then you're going to be lagged here. You see some of the control. If this decelerates, you definitely have a lag here, and if it accelerates, you definitely have that. With connectivity, you may know this deceleration, accelerations ahead of time, right? The preceding vehicle will tell you, okay, I plan to do a deceleration at this time. Then you can activate, enhance your control ahead of time, maybe almost synchronize with this first vehicle's movements. That way, you may not have as much deviation between the actual trajectory and the control trajectory, which is gonna reduce the needing the safety buffer. Right, of course, you're not gonna have that the kind of linear control. So if you're using linear control, everything is actually predicted by the model that we have. The trade-off is like is a card constraint against there.
I'm sorry, but we have to stop right here. But students are welcome to stay for the meet and greet session to ask more Professor Lee. But let's thank Professor Lee for the next.
Thank you. That's wonderful.